for the next week, week and a half, we're going to be doing single body, multi-force. And for right now, we're going to look at a static example. All right, is everybody ready to go? Now, the example should be on the other page. The procedures should be on the page you're setting up. I'll delineate and help you in the beginning, but I'm going to give you the example. So example 1 is kind of pitiful in its simplicity. It's just going to feel like stupid easy. But I want to have a table with a book resting on it. There's my table, there's my book. All right. We are interested in what's happening to the book. So we're going to study the book. All right, so that's our example. Example 1 is to analyze what's happening to the book. Now, I think I misled 5th period a little bit. If I put a book on a table, it's not like I don't know what's going to happen. The book's going to sit on the table, right? I'm choosing these examples because of the reality of what we already know. What you have to understand is that there's something about this framework that creates complications where you believe none exist. A book resting on a table is not particularly complicated. However, in order to understand what Newton's laws are about, you have to understand the way the laws are designed to function. So we're going to use examples that we already know, things we've seen happen before, so that we can figure out how we apply Newton's laws to understand the situation. And it might not be obvious in the beginning why I'm doing it the way I'm doing it, but every example has been carefully chosen. So here's our first thing. We're going to start by drawing a free body diagram. This is the first segment of what you need to know how to do. So drawing a free body diagram, the steps are on the board. I'm just going to read through those steps to you, but I'm going to do this for this example. So a free body diagram begins by trying to wipe away the distractions of the problem and reducing every object in our problem to a dot. Our problem is one object, the book. I reduce the mass of the book to a single dot. That's step 1. Now, the dot represents the mass of the object. It gets rid of its extension and its shape. It also gets rid of the environment that it lives in. But after we've drawn the dot, we're now going to draw an arrow to indicate each force acting on the object. This part requires careful attention to detail. It also requires a ruler, because AP wants them all ruled. That's why I said take a ruler out. Now, on top of that, sorry, that was a pathetic throw. You should expect more from your teacher. When you draw these arrows, you have to draw them to scale. And I know that that's hard because you have no idea what you should draw. I'll tell you this, go big, use the available space. If they give you a square on your test to draw your free body diagram in, use the entire square. Use everything you can. Because once you start drawing in angles and components and trying to figure out what's happening, they can become pretty complicated pretty fast. So, go big. Drawing to scale means being careful to understand that the size of the arrow matters. Let me give you an example. The first of the forces we're going to identify are any fundamental forces acting in our system. And this one's easy because it's always going to be the same force. So when I ask in class, are there any fundamental forces? Be the first one to say, yeah, gravity. That's one you can count on. It'll be in almost every single problem. So in this case, it's no different. The force of gravity is the weight of the object. It is a single arrow drawn towards the center of the earth. Weight. So, my first arrow will be an arrow pointed downwards to indicate the force of gravity, or the weight. Now, when you draw this arrow, you have to label them. And before you write anything down, your book labels it F with a little sub G there. Last year's book was F with a little sub W there. And you can imagine that if you have 2 or 3 forces, you're going to start having a lot of F's. And then you have to break these up into x directions and y directions. That's going to make it complicated. I would encourage you to not do it this way. I like to be as amazingly direct as possible. So if this represents the weight, big W for weight. First letter of each force as the label for the force. Capital W for weight, capital T for tension, capital N for normal. I use a lowercase f for friction because that's conventional, and capital D for drag. And any other force that we have, we'll just use the capital letter if it makes sense. It's much easier. That way when you break them up into dimensions, you can have W in the x direction and W in the y direction. It's easier. Otherwise you have F sub G sub X. It's just too many. So single letter, weight. Weight is the force of gravity. So when we say the weight, we're saying the force of gravity. Okay, once you've covered that, you're going to go down and start looking at contact forces. You have to apply the contact forces based on the definitions I gave you yesterday, not based on how you would like to apply them. This one's really, really easy. We're going to see if the book is in contact with anything, and the answer is yes. It's in contact with the table. Now, contact with the table means it's in contact with a surface. That's a normal force. Normal forces must be drawn perpendicular to the surface. Now be careful. The table's easy, but you have to choose, you have to treat your problem every time by thinking out what direction that surface is pointed. I used the example yesterday with the calculator, remember? So if your surface is at an angle, you have to draw the normal force at that angle. In this case though, come on, I couldn't have made it simpler. The normal force is just straight up, right off the table. Now, how long you draw this arrow is something that you really should stop and ask yourself. I'm looking to the future of this problem already. I'm thinking to myself, are there any ropes connected to the book, any strings or cords? There's probably no tension acting on the book. And I'm also thinking, is the book trying to slide across the table? If it isn't, there's probably no friction acting on the book. And if the book's not moving, there's no drag, because drag is a force for objects that move. So I'm thinking I'm probably on my last force. And I know the book's not going anywhere. So I'm looking to the idea that I think balance has been struck. So in drawing the size of the normal force, I'm predicting in my head that I think the normal force is probably going to be about the same size as the weight. You'll understand why that's true in just a minute when we talk about Newton's laws, but that's why. All right, that is the end of step one. That is a free body diagram. It is a dot with arrows drawn. It's that simple. The arrows have to be labeled, they have to be straight, and you have to be careful to consider direction and size. Everything we do now is not part of the grade associated with a free body diagram. I'm saying that because you may need to draw more than one free body diagram. The one that the graders look at and the one that you use to solve the problem. It is quite possible you'll have to draw another one, because they will be specific about not putting anything extra on your free body diagram. Last year on the exam, the free body diagram was worth 4 points out of 12 for a 12-point FRQ, which doesn't sound like too many until you realize that that FRQ only required 6 points to pass. And 4 of them were about this picture with a couple of arrows. If you could get 2 more points, you pass that FRQ. So please be aware. I am very, very aware of how I want this done. Who had Pagano? Right, did he tell you exactly how to write that essay? Yes. Draw your free body diagrams like this, please. Big, bold, careful. Next, reference. When we actually go to solve the problem, reference is probably the second most important thing you can do. Deciding reference is important. And generally, when we say reference, we're talking about an X, Y coordinate system. So I'm talking about making sure that I choose an X direction and a Y direction that makes sense. There's 2 priorities you should consider. The first is try and choose one that's convenient, that's lined up with as many forces as possible. That's convenient. That's second priority, however. The first priority is lining it up with an acceleration. The book's not accelerating though. So for right now, I'm going to line it up in a way that makes the most sense to me, which is lined up with the forces. This is my coordinate system. When you're actually drawing a coordinate system, what you're really doing is you're drawing in what direction you're going to call positive and negative. You're also establishing for yourself how you'll break your vectors up later. So be aware that choosing reference can make or break your ability to solve the problem. Poor reference and the problem is impossible to solve. Good reference, and typically the problem falls together pretty fast. So be careful about reference. But be aware that reference is arbitrary. I could have just as easily decided this was the y direction if I wanted to. That would be dumb, but I could do it. All right. We'll come back to reference because our next question is going to use reference, but that's generally what you're doing. You're drawing in the x and y. A few things about reference. X and y have to be perpendicular to each other. They have to be. You can't draw an x and a y like this. People do it on my exam every year. They draw the y lined up with some forces and the x lined up with others, but they don't make the x and y perpendicular. Don't do that. X and y have to be perpendicular to each other. Also, if you choose one direction to be positive, the other direction has to be negative. Keep that in mind because that's what we're going to label the forces in positive and negative. All right, this problem has no trig, so step 3 is going to be skipped over. But the way I want you to write step 3 in is a little bit more complicated than just trig. It's resolution of forces. That's what step 3 really is. It's resolution of forces. It's breaking your forces into components. That's what step 3 really is. It's trig, but it's breaking your forces into components. Resolution of forces. Breaking your forces into components. It's what will happen if one of your forces is like that. It's off axis. So step 3, you need to take any off-axis force and find its components. That's what you will be doing. You'll be looking for forces like this that don't line up with x and y, and you'll need to break them into components. You're taking any off-axis force and finding its components. And finally, we make it to step 4, Newton's laws. Newton's laws. There are 3. We are only learning 2 right now. And this problem is an exemplar of Newton's first law. So we are focused right now on Newton's first law. Newton's first law is exemplified by a system that is either at rest or traveling at constant velocity. That's a first law problem. So if your problem is at rest or at constant velocity, it's a first law problem. That's what you're looking for. An object at rest or an object at constant velocity. That's a first law problem. Look, it doesn't mean that it's staying still. So objects that are moving are still first law. That's what constant velocity is. Now, what I'm going to give you are the laws. The first law and the second law. This is the first law problem, so I'm going to give you the first law now. Our next example is a second law problem. I'll give you the second law then. Does everybody understand? So, as a first law problem goes, you try to figure out from looking at your problem whether it's a first law or second law by seeing if the object is accelerating or not. If it's at rest or it's at a constant velocity, it's going to be a first law problem. Now, what that means is you're going to apply the first law. Now, the first law has a colloquial meaning, something that's part of kind of popular culture. And you've heard this phrase before, so I know you've heard, don't write this down, but have you heard the phrase, an object in motion tends to stay in motion? That's a colloquial version of this law. It's missing little pieces, but it's kind of what's happening here. The problem is that things like tend to and stuff like that, they don't really tell you what's happening. So to understand the law, you need a more rigid definition. So I'm going to give you the rigid definition now. This is the one I do want you to have in your notes, and I will repeat it, and I'll go slow. An object will maintain its state of motion. An object will maintain its state of motion. Unless acted on by an external, unbalanced net force. Unless acted on by an external, unbalanced net force. Okay, these pieces are incredibly important and have specific meanings each. Maintain its state of motion means constant velocity or rest. It's maintaining. Its state of motion isn't changing. That's what it means. So maintain its state of motion means constant velocity or rest. External's tricky. You're not going to believe me, and that's okay. External means from the outside. An object can't apply a force to itself. You won't believe that, and it's okay. But I want you to stand up without touching the floor. That doesn't mean standing in your chair, that means you're touching the chair. What I mean is, you can't force yourself to move without touching something else to make it happen. I know it seems weird. You're saying, yeah, I can move my arms, I can flap my arms. I mean, like change your location. Go from one place to another. You can't do it without touching other things. Those things apply forces on you. So for a moment, just understand, Bugs Bunny, when he blows into his own sails, can't make his boat go forward. That's fake, that's cartoons. Objects can't apply forces to themselves. That's why it's funny to watch people walk on the ice, because they can't get traction. That's what you would call this. Gaining traction is grabbing something and using it to move you. So external means from the outside. It's part of this framework. Unbalanced net are two words you probably already know. Unbalanced is obvious. Net means to add up. So when you add up all the forces, if they're balanced, nothing happens to your object. If they're not balanced, something happens to your object. In this case, an object will maintain its state of motion unless there's an unbalanced force acting on it. That's what this law is about. It's telling us that objects that are at rest, they might have lots of forces, but they're balanced. That's what this law is about. Now, there is a mathematical way of writing this law. It's not an equation. It's going to look like an equation, but it's not. It's a set of instructions. The mathematical way it looks is like this. It's the summation. It's an F with a bar over it equals 0. This is Newton's first law, written mathematically. This is not an equation. Yes, sir?
Where do like the symbols represent?
I'm gonna talk about every one of them.
Because you see that in math too.
I know. I'm gonna tell you what every one of them means. The sigma is a symbol at the front. It's a summation symbol. It means to add up. So specifically in mathematics, it's the sum. Now, this is important. This says to add up all the forces. That's what the F stands for. But the bar on top reminds us that force is a vector. So it says to add up all the forces, taking into account their direction, and set that equal to 0. This is a set of directions. To add up all the forces, taking into account their direction, and set that equal to 0. Newton's laws are instructions. They are instructional. So we're going to apply Newton's laws to this example. Looking at this example, I do want to point out that there's nothing in the x direction. So although I should be careful and say I should do net force in the x and net force in the y, they're both going to be 0 because it's a first law problem. The reason we have reference is so that we can take our forces and work in one dimension. Remember, we are only one-dimensional math. So all of our problems have to be one-dimensional. There are no forces in the x direction, so I can completely ignore the x direction. But there are forces in the y direction. So this says to add up all the forces in the y direction, taking into account their direction and set it equal to 0. So if I do that, I'll point out that the normal force is in the positive y direction, so positive n. The weight is in the negative y direction, so minus weight. Those are the only forces in the y direction. I've added them all up, and I'll set them equal to 0.
Can you repeat that last part?
Yeah.
Positive.
I start with n. It's pointed in the positive y direction, so I put positive n here. It represents a force in the y direction. Next, the weight, which is also in the y direction but is aimed downwards, requires that I make it negative. Since I'm applying Newton's first law, yes ma'am?
Do you want us to write this on the sheet yet, or are you doing a different one afterwards?
This is part of the example. This is how to apply Newton's law. I'm not sure where you want to put this.
Oh.
I put some of the stuff about, what the summation means and taking account direction on your instructional sheet, but I'd put like how it applies specifically to this example, I'd put that on the example sheet.
Okay.
If it were me. And here's why. And this is what I was going to answer anyways, so I'm glad you asked. Newton's laws are instructions. When Newton's laws have been used correctly, they create a custom equation that is designed to solve that problem only. That's what's going to happen here. For every single Newton's law problem, we're going to create a relationship that applies to this custom arrangement. Every one of them is different. This equation doesn't work anywhere else but in this example. This one example where we apply Newton's laws to this situation. So you think that we've solved and created something that we can use over and over again. That's not true. The only thing we can use over and over again is Newton's law. We will apply it, and when we apply it, we will create something custom for that problem. So this n minus w equals 0. It fits the book on the table. I mean, yes, it'll also fit the phone on the table, and the water bottle on the table, and the basket on the table. But if I choose to change the problem, it won't fit anymore. Now look, the best way to see this in action is to see it over and over again. Let's try another one. Let's get back up to the top and try again. I have 15 minutes. You want me done in 14, right? So let's go. Ready? I'm going to set this problem up. This is a being pulled across the ground. Let's make 3 assumptions about the wagon. First, let's assume that the wagon is not experiencing friction. I want to make it somewhat simple right now. So here's the ground. Here's the wagon. And I'm pulling on the wagon by using its handle. The handle's making an angle of theta with the ground, and there's no friction. Before I go any further, will we all agree? You pull on the handle, the wagon moves. Accelerates, right? Starts from rest, speeds up. So if it was at rest and I pull on the handle, I will speed it up. We all agree? Could I pull hard enough to lift the wagon off the ground? Sure. Let's say I'm not. Okay? I'm just pulling it. These are the kind of reasonable things you should think about when looking at a problem. So I'm going to assume we all kind of come to the conclusion that this system is going to accelerate that way. Would you agree? That makes the most sense. Step 1, free body diagram. I'm going to reduce my wagon to a dot. Step 2. Oh, sorry. Of free body diagrams, the next thing to do with the free body diagram is to begin to draw arrows. And you draw one arrow for every force acting on my system. Let's start with I don't know, gravity seemed like an appropriate place to start. So gravity is a force of weight acting downwards on the object. I will draw a single arrow downwards to represent the weight of the object. And I will label it so, weight. Yes?
Is the line always about that same size when you draw it, or does it?
I can't tell you that. I don't know. Yeah, sure. Always about that size. I always start with the weight and I make every other force relative to the weight's size. Because here's the next thing. Do you realize that I'm pulling upwards on the wagon a little bit? All of you agree with that? Normal forces are responding forces. They respond. They're responsive. If the wagon is pulled off the ground, there won't be a normal force. But does the ground have to support the full weight of the wagon now?
Yes.
No, because I'm pulling up on it some.
Oh,
I could pull up enough to lift it off the ground, but I'm not. But I am pulling up a little bit. The normal force won't apply more force than is necessary to keep the wagon from sinking into the ground. That's why there is a normal force. The book on the table can't push up harder than the book is pushing down. But if it doesn't push enough, the book falls through the table. Now that could happen. You could stack enough books on a table to collapse the table, where the table can't provide any more normal force. But generally, like the wall, you can push on the wall. A lot of you could push on the wall, and the wall won't fall down. It'll keep applying a normal force. It'll keep increasing the normal force until you exceed its ability to do so. But it doesn't mean it supplies all of it. If you barely touch the wall, it'll only push back a little bit. So this is the case here. The ground doesn't have to apply as much force as the weight of the object, because I know I'm also pulling up on the wagon a little bit. This is why dealing with size of vectors isn't easy, because you have to think it through. I know that there's another force being acted on right now, that there is a tension. The tension force comes from me pulling on the handle of the wagon. It's a tension because it's a pulling force. The conduit is the handle. That's my connection to the wagon. It's a clear tension. And the tension is both to the right and upwards, which means that this force is not only causing it to move to the right, but it's also lifting it a little bit from the ground. Yes, sir?
so does it matter how exact that like angle is of the arrow?
If I were you, if they give you an angle, I'd use the protractor and get it close. But if you know it's less than 45, make it less. If you know it's more than 45, make it more. Don't worry too much more beyond that.
And, okay, I was also going to say length.
The length of the arrow was not arbitrary. And I'll show you why I drew it this way in a moment. But just to kind of have a little foreshadowing, the tension pulls up a little bit and over a little bit. I didn't draw those arbitrary. Do you notice how I drew the up one to go from about here to about the tip of the arrow here? That's how long that part is going up, and this part is how long it's going to the right. I'm trying to consider the fact that these two have to balance that. Okay? But that's a little foreshadowing. That's a free body diagram right here. That's done. Coordinate system is nice. It's necessary to solve the problem, but when you're asked to provide a free body diagram for a grade, this is what you provide. But now let's go to part two, reference. You need to draw a reference system that will help you solve the problem. 2 priorities here. Try and align it with as many forces as possible, but always align one of the directions with the acceleration. That is the first and number 1 priority. If your system's accelerating, draw one of the directions in the direction of the acceleration. That should be your number 1 priority. So I am going to draw a dotted line to represent the X direction horizontally, because that's the direction this thing is accelerating. And every other part of my coordinate system will come into place based on the direction of X. For example, negative x has to be in the opposite direction. Has to be. I don't get a choice. Positive y has to be straight up. It has to be perpendicular. Negative y has to be in the opposite direction of positive y. The angle in my diagram has to match the angle in the picture. The angle is given me relative to the horizontal. It's accelerating horizontally. That's my coordinate system. Drawing the coordinate system is challenging. It seems easy, but it's the most important decision you can make. It can make or break your ability to do the problem. Now, the next parts of this problem are the trig. And I'm not going to belabor the trig right now. We're going to take a look at a quick version of the trig. But I'm not actually going to do sine and cosine. The next segment requires that you take and resolve your forces, which means to break them into components. Look, in your procedure, breaking forces into components means triangles. You are going to draw a right triangle around any force that is not in the x and y direction. You're going to draw a right triangle around any force that is not in the x and y direction. If you want my opinion, the best way to do this is to wrap the triangle around the given angle. You're going to break your forces up into components. You're going to draw triangles for every force that's not in x or y. You're going to draw a triangle around every force that's not in x and y. I've said that like 6 times. I'm hoping you're done. I would wrap your triangle around the angle. Here's what I mean. Do you see the angle? Right? You all see it there, right? I'm going to start where the force starts, and I'm going to end where the force ends by wrapping a triangle along x, turning and going along y. Has to be a right triangle. Components have to be at right angles to each other. And do you see what I mean by wrapping it around the angle? I've created a triangle by wrapping my components around the angle. Now, what I've really done is I've created the size of Tx and the size of Ty. I have found out how much of the tension is in the x direction and how much of the tension is in the y direction. And it should not be lost on you that there's trig here, right? Sine and cosine. You see it clearly? Every one of these is going to be different.